Hello and welcome to the iRevise Supplementary Series for A-Level Physics. This is video 1 of 2 of an Astrophysics series. Most UK A-Level courses involve some sort of astrophysics. A lot of them have similar topics. There are some particular topics which are only focused on in particular exam boards. But what we will discuss in this video is cosmology, meaning Big Bang Theory. We'll talk about redshift. We'll just talk about how we've got theories of the universe and how we use redshift to figure out recession velocities, that sort of thing, how we calculate it. Okay, and then we have the Hubble constant, these types of calculations. We'll also take a look at using Wien's law. Okay, and I think some exam boards need you to know what the spectral class is based on temperature, based on wavelength, this sort of thing. I know some do, some don't. You'll see in the questions. We'll take a look at Stefan's law, luminosity, whether it's explicitly in your curriculum or not for your exam board. We will be looking at the inverse square law. A really good exercise would be for you to take Stefan's law and use that to derive an inverse square law. You'll see kind of how that works. Okay, we'll be taking a look at specifically angular resolution and telescopes when it comes to lenses. I know some courses cover lenses in greater detail than others. We will just be looking at what that means in terms of angular resolution and telescopes. We'll talk about parallax and that sort of thing. Okay, what we will not be covering, we'll do this in another video, we'll be looking at Kepler's laws, calculating the mass of a star, calculating the mass of a satellite, the universal law of gravitation, that sort of thing. That will be combined in with the video on gravitational fields, gravitation, and electric fields. Exam boards covered in this topic are Edexcel, AQA, the OCR Physics A and B, WJEC with some Eduqas, and the Cambridge Pre-U. So we've got a lot to get through. Let's get on with the astronomy. Okay, to start things off, I've got a 2013 paper 3 from the Cambridge Pre-U. Define for a star the terms luminosity and luminous flux. Well, luminosity, I think in our everyday language, we like to maybe equate that with brightness, and I think that's not really a wise move. You know that the unit for luminosity is watts, therefore it's the power of the star, how much energy is being given off. Okay, luminosity is power. Brightness, we've got, you know, our apparent and absolute magnitude. We've got other ways of measuring brightness. Okay, but luminosity is the power. Luminous flux, well, the word flux actually just means flow. Okay, it's how much of this power is flowing through a certain area. If you think about magnetic flux, we're talking the flux density. We're talking about how much of the magnetic field lines are going through a certain area. It's the same thing with luminous flux, except in the case of flux, because we've got a star, we are looking at a certain surface area determined by the radius, determined by the distance that we are measuring from that particular star. And so the further away from the star, the greater that radius, but also the greater the surface area of that sphere. Okay, so how much of that power is going out in all directions through the surface area of a sphere at a determined distance? Just like magnetic flux is the magnetic field strength per unit area, so luminous flux will be the power per unit area. Okay, what information can be gained from the color of the star? That's the temperature. What can be learned from the absorption spectrum of a star? Well, we can do two things. We can figure out what its composition is because we'll know the spectral lines are indicative of certain elements. We can also determine the recession velocity, how fast away this thing's moving away. We get that from the redshift, don't we? Okay, and then some calculations here. Calculate the velocity of recession, and we're going to get that from the redshift, and then to calculate the distance the galaxy is from the Earth. Okay, we know that the redshift is equal to the ratio of the velocity with the speed of light. That's also equal to this ratio of the difference in wavelengths to the laboratory wavelength. Make sure you substitute in the correct laboratory wavelength where it needs to go. The small number will always go there because it's the laboratory setting. Okay, the redshifted one will always be larger. That's what we're subtracting. Anyways, you get it all in there. You get an answer of 1.53 times 10 to the 7. You should always get something which is less than the speed of light. Okay, and then we plug it in here to find our distance. We rearrange our Hubble equation, and you just take that and divide by the constant they give you, and you get 6.69 times 10 to the 24. That's in meters, of course. By the way, this distance here is something like 700 million light years away. Let's check the answers, see how we've done. Okay, so yeah, we've got the calculations done. That's correctly. Luminosity is power radiated by a star. Luminous flux is intensity of radiation. Okay, so I think we had said that, but I just tried to explain a little bit about what that really is. But it's basically the intensity. You can find out the surface temperature of the star. You can find out the elements present. That's what I mean by composition. Okay, maybe be a little more detailed than I was. And then, of course, the recession speed, which we've just calculated here. All right, I've got an AQA Paper 3, Astrophysics from June 2019. Right, they're asking in this question here about chromatic aberration, and they want you to draw. I can't draw a diagram because they won't let me draw on these papers, but I can show you kind of how it should look, right? I just do a search here for chromatic aberration. I want to point out how horrible this diagram is, why they've decided to have green lines outside of the blue. Green should be in the middle. This is a horrible diagram. This is a much better diagram. You can see here that because blue's got a shorter wavelength, it's going to be refracted at a greater degree than the red, and the green should be in the middle. Here's another diagram of how it might be, and you can see that the color points end up meeting in different bits, and so what ends up happening is you can see this sort of thing where things aren't focused the right way. Maybe you've seen this on a projector before. Okay, it can happen in everyday light too. Okay, this ice sculptor is bending the light at different rates. Okay, apparently this is an example too. You can kind of see it with some photographs sometimes. And anyways, that's just the diagram. That's how it should look. So the red is furthest out, blue is closest in to the lens. That's how your diagram would look. Okay, so let's move on. Okay, a Cassegrain telescope uses mirrors, right? Let's take a look just real quick at some ray diagrams for a Cassegrain. You might have something like this, right? So you've got a curved mirror here, and it's going to reflect back to another curved mirror, which goes into the eyepiece. This one's kind of interesting. You could draw something along these lines if you need to draw. I think this question is just a simple. This question is just simply wondering what kind of mirrors are we looking at here. So the primary mirror is a convex mirror, or is it concave? Yeah, these ones here, there you can see they're concave. Yeah. So we want concave, and then the other one's convex. I'm going to guess second row, concave, convex. Let's have a look at the mark scheme while we remember. Yeah, concave, convex. Okay, and by the way, so 2 rays brought to red focus and 2 rays brought to blue focus on the primary axis, and the blue ray is closer to the lens than the red ray. Okay?
Coming soon to Blu-ray.
And there's some other bits here on the right. You can look, just pause and have a look at that, okay? Okay, on to the next question here. We've got 2 different telescopes. We're comparing an optical reflecting telescope and a radio telescope. We can see the diameters. We can see the wavelengths that are detected, okay? Discuss similarities and differences between optical reflecting telescopes and radio telescopes. Your answer should include references to structure, positioning, and collecting power, okay? So you could look at that and say, hey, there's 3 things we can discuss, 2 marks each, but read on further. Go on to discuss which telescope will give a more detailed image. Right, okay, so structurally, we know that a reflecting telescope, we need to reflect the light back onto another small mirror. It's kind of like a Cassegrain telescope, isn't it? Okay, and then back into an eyepiece in which it's magnified. Whereas radio telescopes, we see a much larger diameter. We're talking about big dishes. You know, the maybe you're familiar with the observatory in Puerto Rico that you know, has finally met its demise after decades of research from it. It's the one you see in that Jodie Foster movie, Contact. Anyway, given the inability to write on the AQA papers, I'm just going to go to the mark scheme, and we'll see what they say here. Okay, so structure. Both use a parabolic surface. Okay. The difference is the radio, there's no secondary reflector. Okay, the detector is placed at the focal point of the primary, so you can see here in the picture how everything is. There's a little detector up there in the middle. Okay, the detector at the Arecibo laboratory, which is no longer in existence, also gained a lot of fame from being in the James Bond movie GoldenEye. I won't spoil the movie for you, but it's quite a climactic end to the movie. It takes place at the observatory there. Yeah, okay, anyway, moving on. Similarities in positioning. Both are capable of being used on the Earth's surface. That's true because the range of visible light and the particular part of the radio spectrum that is being looked at doesn't get absorbed by clouds or even just through the atmosphere. Presence of both on the planet can be inferred if you talk about the altitude, them being maybe at different altitudes. That's assumed they're on the Earth's surface. Okay, but the key difference here is we're not having these telescopes floating around in space. We don't need to. Okay. There is a problem with the reflecting one, of course, because we've got light pollution. So they need to be built, up high on mountains, kind of away from the city, away from, there's less of an atmosphere to go through, so less distortions, that kind of thing. In terms of radio telescopes, they don't have light pollution, but they might have this radio wave pollution. You wouldn't build a radio observatory, say, near like an airport or some place where you've got a lot of, communication traffic, okay? Collecting power, well, you saw that the diameter here is much, much larger. It's just about 3 times larger, and so that means it's kind of a much, much larger collecting power, and so d squared is how you get collecting power, okay? And if you wanted to, you could do a ratio here. You could take the 110 squared divided by the 39.3 squared. You see there, 7.8, that's what they're talking about being 8 times greater, okay? So you could do some calculations if you like. All right, that might be a good thing. That's an easy way to spread out, get some marks. And then resolving power, okay? So telescope B has a large diameter, but it's extremely large wavelength means generally low resolving power, okay? Because you remember your formula here, and this is the Rayleigh criterion. If you take a look at the Rayleigh criterion, by the way, this is Hyperphysics, lovely website. Check it out. Just do a search for Hyperphysics and it'll pop up. But here's your Rayleigh criterion. This is obviously they're talking about single slit, and they're talking about maybe for lights here and diffraction and stuff. But I think this formula still holds true. You know that the resolution is found by dividing lambda, the wavelength, divided by the diameter of the this, and it means that you're going to have not as much of it. And if you've ever seen pictures of radio telescope work, they are not as detailed as what you'll get from a light telescope. That's true. Anything else here? Evidence of some calculations. Yeah, okay, so remember that they give you a range of wavelengths here. So what you could do, you can compare the minimum wavelengths for each, you can compare the maximum wavelengths for each, and you can kind of see there what we're talking about, resolution power measured in radians. Okay, so I think there's 4 things you can talk about, and if you can mention 1 or 2 things for each, you'll have more than enough to get the 6 marks there. Okay, just make sure you're practicing this sort of thing. Moving on to number 2 here. Right, so we've got a comparison of the 4 brightest stars in the Canis Minor constellation. We can see here that 2 of these stars are spectral class K. We've got a range of apparent magnitude and the associated absolute magnitude. Discuss with reference to the Hipparcos scale why many star maps only show 2 stars in this constellation. Okay, so if you take a look at the apparent magnitudes, you recall that 1 was supposed to be the brightest, and if you got all the way down to 6, that was the faintest. And you can see here that these 2 numbers here in the 4 are probably very dim. That's the gamma A and the HD. They probably won't appear on the map because they're not going to be bright enough. Okay, on to the second part. State and explain which star in Table 2 has the most prominent hydrogen Balmer absorption lines. Right, just in case you need a little refresher, here we've got some spectral class of the stars, and you've got kind of what their colors are, okay? And you can see here too their effective temperature. So the B classification are quite hot, and those will probably be the only star that's going to allow for absorption lines for the Balmer series. Deduce which star, gamma A or HD, has the larger diameter. Right, so if you take Stefan's law, okay, what we know is that these temperatures are going to be the same for both stars, and we know that this is a constant here. So what we can do is we can say luminosity divided by area is going to be some constant, and we can say that the luminosity of this Gomeisa as a ratio with its area, we will have a ratio of the luminosity of this HD with its area. And then what we can do is we'll say, hey, let's do a ratio of luminosities with a ratio of areas. Now, which of these had a larger absolute magnitude? It was gamma A. So if gamma A has a larger absolute magnitude in luminosity, if this ratio is to be the same, then it must also have a larger area and therefore a larger diameter. You could look at it that way, but basically it stands to reason. If they've got same spectral class, temperature is not a factor, and when we put them at absolute magnitude and place them equal distance away from Earth, and one of them is a little bit brighter, then that must mean that it is also larger, therefore. So you don't need the mathematics to describe it. Just make sure you get your 3 points in explaining what you would say. Okay, and moving on, astronomers recently used the radial velocity to discover an exoplanet orbiting HD 66141. Describe the main features of the radial velocity method in detection of planets. Well, typically, if you've got a star and a planet, I know in our solar system, maybe we don't see this because 99% of the mass of the solar system comes from our sun. But maybe if this is a smaller star, larger planet, maybe they have a common center of mass somewhere. And even if it's close to that star itself, we can see as they rotate around this common center of mass, okay, we will see that this star will be moving towards us and away from us if we are looking in the plane of the orbit. We will see when it moves forward and away, there'll be a Doppler shift, there'll be a red shift coming towards, a blue shift moving away. It's orbiting with something, and if it's not another star, which obviously we would see, we would have to assume it is a large mass, which is likely a planet. Calculate the distance from Earth to Procyon. Give an appropriate unit for your answer. All right, so this is the formula that we're going to use. We need to plug in some values. Okay, so we have apparent magnitude and absolute magnitude. Remember that we're doing apparent magnitude minus absolute magnitude. Okay, this d here is the distance from Earth. Right, so we'll do a little math here. If we bring this out over here, we'll have log d over 10. So we'll do 2.31 divided by 5. Make sure you get the negative out in front, because what we're going to do now is we're going to take the inverse log of both sides. So on the left side, okay, if I didn't have the negative there, then I would have had a number maybe larger than 1. Okay, because this is negative, this is going to make this number here, when I do the 10 to the power of the negative, it's going to make a number less than 1. So that's very important. Okay, now d is, we're going to bring 10 times that, and we should get 3.451. What's the unit of this whole situation? Do you remember that our definition of the absolute magnitude is what would the brightness be if we were 10 parsecs away from Earth? So our answer is parsecs. Okay, taking a look at the mark scheme for our answer. The Hipparcos scale is from brightest 1 down to 6 dimmest, and these guys are kind of dim, and only the other ones would be seen, so that's fine, I think, for 3 marks, okay? We had said Gomesia was B class, and it's going to be the one hot enough, right, okay? Gomeisa. If you don't write, you can just say the B class star if you like. You don't need to write the name, but why wouldn't you copy it? Okay, and then 2.3, right, so you need to mention that it's the similar temperature, and therefore we don't need to worry about that. You can kind of show the proportionality, the math bit, or you could just simply say, hey, it's got a larger absolute magnitude, and that means, because of Stefan's law, it's got a larger area, okay? Right, how do we detect exoplanets? It's the Doppler shift in the light from the star, and this is due to the star planet orbiting around a center of mass. So you'll see the star's not just sitting there, but you'll see a kind of an alternating red and blue shift. You could figure out the period from there, and from that you could calculate the mass of the planet, couldn't you? Okay, and then the last bit is just use of that formula, and as we say, you just plug it in, rearrange, and you get 3.45 parsecs. Well done. Moving on to number 3, we have an HR diagram. Label the absolute magnitude axis with a suitable scale. Most HR diagrams you find on the internet compare it with solar luminosities. I would imagine in the AQA syllabus, if they're asking you this, that they've discussed and they tell you what you should know what this range would be. Okay? The second part here, label S on the position of the sun. Well, we know we're a little bit above 5,000, maybe 6,000. I'd say that we're somewhere around here. We're still, it's red down here, and then it gets yellow, and then we're getting into the white and the blue. But we're about 6,000, so I'd say somewhere around here. Draw a line on the HR diagram to show the evolution of a star similar to the Sun. Okay, well, we're in the main sequence here. We're going to come on out into the red giant area, and eventually after the collapse, it will become a white dwarf. So you'd have a line moving down there. And then label with a P the position of the HR diagram of a star much redder and with a greater power output than the Sun. It's going to be red, which is somewhere to the right. It's going to move over. Now, if it's got a larger power output than the Sun, it's going to have to be larger. So, it might not necessarily be a giant, but it's going to be up over here, up and to the right, isn't it? How are we doing on the mark scheme so far? Okay, so they're saying scaled from plus 15 up to negative 10. The plus 15 is down here at the bottom on the absolute scale, and the negative 10 is up there. Okay, our sun's between 5,000 K and a horizontal section of the bottom line of the main sequence. That's where they want us to draw it, with main sequence, within main sequence and at correct absolute magnitude. Okay, so however you've done your scale here, you'd want your absolute magnitude to be 5. I guess that's what it is for the Sun. Maybe you need to know that. And then your temperature, you're going up between a line between here, they say 5,000, and this horizontal section. So somewhere before that horizontal bit starts, somewhere in this area. And I imagine you want your plus 5 to be that on your scale. And the path, here's the line that they've drawn for the path. Now, I'm not sure what this line is coming in from. It says a line coming in from the right to where you've drawn your S. I imagine this is where a protostar might be. It might be kind of large, and then maybe when it condenses down on itself and it starts to get hotter. I can see it moving to the left and getting hotter, definitely, but that would be my guess. It's a protostar thing. Hey, that's an AQA thing. I'd not seen that before, so those of you studying AQA, I'm sure you've seen that, but I think everybody else can agree with the path here, going up to the red giant and then down into white dwarfs, okay? Okay, and as we said, point P is going to be up and to the right. Part 5, a star much more massive than the Sun may become a supernova and then a black hole. Discuss whether supernovae and black holes can be placed on an HR diagram. Well, this is an interesting one. Does it make sense to put black holes and supernova on a HR diagram? Well, for one thing, supernovas don't really last very long, so it'd be very difficult to just place it on a spot and say, yeah, here it's there. I don't know if the temperature is constant. We definitely know that the absolute magnitude, they're going to be incredibly, incredibly bright, and they're probably going to be off the scale. Okay. Now it's the opposite thing with black holes. They're so dense that light, their escape velocity is greater than the speed of light. Not even light can escape. So how are you going to measure the brightness when you've got no light coming from a black hole? So that would be my thoughts. What do they say here? Absolute magnitude of a supernova, right, beyond the scale, right, like we said. And then also, I'd said that they are short-lived, and so we can't really say. But it's either one or the other about that, okay, about the supernova. Okay, the temperature of a supernova is peak. It's too high. Yeah, it's going to be, again, it's going to be off the temperature scale. It's going to be well above the 50,000 K, isn't it? So you're talking about way over here, up and to the left, way off the scale. That doesn't make sense. And then you've got a choice here for the black hole. Either the escape velocity is greater than c or it doesn't emit any light, something like that. And then a fourth possible thing you could say, but there's maximum of 3, temperature of the black hole would be too low. They're going to be incredibly low temperature, and of course they're going to be off that scale, aren't they? Okay, so there you go, 4 things to talk about. Okay, we've got a comparison here of 2 galaxies. This looks to be like a bit of a math question here. Discuss whether this data is consistent with Hubble's law. Right, so here we've got the data from the question. We know that the redshift is defined as a ratio of the galaxy's velocity with the speed of light. It's also this delta lambda over lambda with your laboratory lambda here in comparison with what you see as the shift. We also got our equation here from Hubble's law. Right, what I'd like to do is combine these into one thing here, right? So I'm going to put... Let's call this Galaxy 1 and Galaxy 2, and I'm going to say, hey, if I rearrange to have VD over H naught, so I've got V1 over D1 equals V2 over D2, we can say. Yeah? Well, what is V? Well, V is going to be the Z times the speed of light. Okay? We don't have any wavelengths mentioned here, so we don't have to worry about that. It's just going to be Z times the speed of light. Now, the speed of light's a constant, so we don't need to worry about that. And we actually end up getting... Z1 over D1 equals Z2 over D2. Okay, so that's pretty straightforward. Okay, and I just plug in the values here. As you can see, I didn't worry about any times 10 to the 3, times 10 to the 7. That's all going to cancel out. That's all going to come out in the wash anyway. Not worried about changing light years. It's just a ratio. It'll be the same units on either side. Okay, so, whether you change it, doesn't matter. We get 0.705 and 0.9375, and we see that the right side does not equal the left side, and therefore I would say that this data is not consistent with Hubble's law. And let's go on here. Quasars are the most distant measurable objects. Discuss one problem associated with the determination of the distance from the Earth to a quasar. Okay. Well, it's pretty far away, so I would imagine the inverse square law has something to do with it. I am not all too familiar with the AQA syllabus, so let's just, in the interest of time, move on and see what they say. Okay. So distant quasars are faint. A type 1 supernova, which would, which is a standard candle in an associated galaxy, would be very faint. Okay, I'm not sure what they mean by supernovas in there, but maybe that makes sense to AQA students. You could talk about inverse square law, or you could talk about due to dark energy or the expanding universe. If we were to use Hubble's law or inverse square law, it's not reliable over large distances. Yeah, it does break down. It does seem to be not constant depending on how far you go. So if you've studied the quasars, maybe that makes a little bit more sense to you. Let's scroll up and take a look at correct use of Doppler equation for both galaxies, correct use of Hubble's law for both galaxies, right, which is what we had done here. Okay, Doppler, Hubble. I've put them together. It's just two calculations. Justified comparison leading to conclusion. You could calculate You could calculate these velocities first, in kilometers per second per megaparsec. Then you could use using the Hubble constant, plug it in, and you could see, hey, does the Z's matter? I think what I've done here is I've done Z over D ratio, and I've compared. That's what they've done. So there's different ways you could do this mathematically. Pause and read the rest there if you like, but I think we've done that. Okay, and this is an Edexcel paper 2, Advanced Physics. It's from 2018. Okay, in 2016, the Breakthrough Starshot Initiative was announced. This project intends to send a small fleet of probes to Proxima Centauri. That's the nearest star to the Sun. This journey should take about 20 years. Okay, so the intensity in watts per meter squared, right? So this is intensity as in, power divided by area. Okay, for Proxima Centauri. Yeah, is 3.25 times 10 to the negative 11. They give us the luminosity of the Sun. Show that the luminosity of Proxima Centauri is about 0.002. Okay, and here's the luminosity of the Sun. All right, so they've given us the distance to Proxima Centauri as well. So I think we can just use this to go and calculate the I've said power here, but power or if you want to write it as luminosity, that's fine as well. So the luminosity is going to be the intensity times the area. Okay, now look what I've done here. I thought I'm multiplying by this whole area, but I'm about to square this. Watch what you're doing. You're only squaring the distance, not the 4 pi. So I get a luminosity of 6.53 times 10 to the power of 23. So if we do a ratio, we'll take that number and we'll divide by the luminosity of the Sun. And I get 0.0016917, and I would say, yeah, that's roughly 0.002, wouldn't you? All right, let's move on to part II here. Right, so determine whether the surface temperature of Proxima Centauri is consistent with its position here on the HR diagram. Okay, well, we've just calculated that luminosity, and so now we've got this. They've given us the radius. Right, so we're going to rearrange. We'll do luminosity divided by this 4 pi r squared. Okay, it might be handy to have the number from the previous question stored in your calculator. If you see parts I and double I and that kind of thing, it saves you typing it in the calculator. It's already there. Just save that as an answer. Come up with a system of every other, go up the alphabet or whatever your calculator lets you do. But it'll just save you time and you've got it easily there to punch in for the next calculation, and I think that can be very useful. Okay, so there's the radius they've given us. I've got it there. Okay, so I get a temperature of 9.5 times 10 to the 13. Of course, we're going to have to take the fourth root for this. So you could do the square root twice. Maybe your calculator lets you do a fourth root button. But I get 3,124 Kelvin. Okay, what were they saying about this? Whether the surface temperature is consistent? Well, the luminosity compared to the sun was basically 0.0017, wasn't it? 0.002. Okay, so that's basically, let's say, 2/1000ths. Yeah. Now here we've got 1. This is the ratio. This is a ratio of luminosity, with our solar our very own sun's luminosity. So 1/1000th would, okay, let's see here. This is 100th. 1/1000th would be somewhere in between here, 10 to the negative 2, 10 to the negative 4. 2/1000ths, 1/1000th, it doesn't matter. We're talking order of magnitude. So we stroll along. We are at about 3,100. So it's right about here. It seems a little bit at the edge, but it seems to be fine with me. What do they say about that? We've used the formula. We got the answer. That's fine. Statement relating calculated values to the main. Yeah, I didn't say anything. I was talking to you about it, but I would think you would write a statement saying, hey, it seems to be on the very edge, but there's a couple of dots kind of in there. I'd say that's legit. And then here's our calculation before. That's fine. We did that. That's good. Okay, and this is a paper 2 all right, and this is a paper 2 from Advanced Physics 2 of the Edexcel. This is a June 2018, and there's a question part. There's a question part B. The composition of the star can be determined by the analysis of the absorption spectra. Why are there different frequencies missing from the spectrum? This is the absorption spectrum. Why are there frequencies missing? Okay, well let's say we've got a light source. We've got a sun, and it's going to be giving out a whole spectrum, and there's a cloud of the gas along the way. Some of the atoms, some of the gas atoms will be absorbing energy at certain wavelengths, and we know that if you've got an atom here, if you've got an electron here, if it absorbs a certain wavelength of energy, we're talking at a certain wavelength, a certain frequency, it will have the exact amount it needs to be promoted into an excited level. It'll move up to a different orbital, a higher orbital. Okay, and so those wavelengths of energy are absorbed, they are taken in, and the rest of the light passes through. So depending on the orbitals that are available and the electrons which are already, if these orbitals are filled or not filled or whatever, that will determine where these lines get drawn in. And there's very characteristic lines from certain excitation for Balmer series. We've got some other series for hydrogen, for the example of the different orbitals that those electrons could inhabit, and this is going to be something which is unique for every single element. It's like a fingerprint, if you will, to determine what element is present in that gas. Okay, I think, have we got that? Let's move on and see. Atoms have fixed or discrete or specific energy levels. Okay, I mentioned that. Again, I'm kind of just roughly going through and explaining. You're going to have to craft your answer to make sure you're nice and articulate. Electrons get excited by absorbing. Okay, so photons. In this exam board, they're very key on you writing photons. Make sure you are mentioning photons. I have it underlined. The energy of the photon absorbed is the difference in the energy levels. I think I had alluded to that. And only certain transitions are possible, so only for certain photons get absorbed. Yeah, okay. And the set of frequencies absorbs depends on the element, we had said. Okay, I think I've covered everything there. Answers in terms of emission spectra can be awarded marks 1, 4, and 5, because here they're talking about electrons getting excited and moving up. Okay, so don't talk about emission spectra. That's the opposite process. The emission spectra is when these electrons jump back down. Okay, now like I was saying, I'm just going through and explaining. You're going to have to make sure you get each of those points and make sure you're understood. let's answer this question. Describe how the distance to nearby stars like Proxima Centauri is determined. Okay, very basically, if this is the orbit of the Earth and we've got 2 times here, maybe January, maybe June, but 6 months apart, wherever we can line up, and if Proxima Centauri is out over here, okay, we'll have a line of sight. I'll draw my lines this way, but you know the light's coming. You don't need arrows for these diagrams, but you get what's going on. Okay, so what we see on one orbit, there'll be some stars in the background, and then we have a revolution halfway around the sun, and we'll have different stars in the background, and you can see how far it's shift. This is known as the parallax method.
Tell the Guardians, it's parallax.
And this is how we can figure, you've seen in other exam boards, you get your angle subtended here, and we can figure out what that distance is using that calculation. I'd say something to that effect. So they say stars viewed from 2 positions 6 months apart, or stars viewed from opposite ends of its orbit, diameter about the sun. Yep, good. Okay, and the change in angular position against this background. Yeah, it's very basic in Edexcel. It's not like these OCR and AQA exam questions, is it? Okay, and I've got an Edexcel paper 3 here. This is a question about luminosity on the stars. So that they've got this is a suggested relationship here. Okay, and so explain why a graph of log L against log M would give a straight line. Well, if you take the log of both sides of the equation, what we'll do is we'll use our rules of logarithms, and we'll split this up. Now, if I've got a log of m to the p, that's the same as saying p times log m. Now, if you take a look at what's going on here, this is the same thing as this would be a c, because log of some number is just going to be some number. Okay, and p here acts as the gradient. Log m is the independent variable. We've got a line that matches the y equals mx plus c or mx plus b pattern. So there we go. Now they want you to plot a graph. You're going to have to do some logs on your own. I would use these columns here to calculate the log of m and the log of L. We'll go right to the mark scheme to see how that should look. I'm not going to take the time. So here you would fill in the log values like I said. Okay, you could do ln values, I suppose, but I mean it's pretty clear they want you to do log. So either way, and you should get a graph that looks like this. You get some points here. Try this on your own. Here's the equation that you get, and if you, just for fun, if you wanted to double check on Excel, you'd probably get your p and your L values there. Okay, so it's 5 marks. So you get 1 for line of best fit, 1 for the plots, 1 for the scales, 1 for the log values in the table, and 1 for labels on your axes and the units. Okay. And while we're here, we'll go back up and we'll see that that's how we got a y equals mx plus c. That's why it's a straight line we saw. All right, moving on, last part here. So determine the values for P and L. Well, we saw them just a moment ago when we were looking at the graph, didn't we? And state the mathematical relationship between L and M. So again, you're just going to find those 2 values and plug them in. So we'll see what they say. You're going to determine the gradient on the graph, and they want the delta x to be larger than 0.6. I would say you want your triangle to be fairly large, okay, for whatever graph you use. So there's a graph you can do where it's log divided by the w, and then there's another one here where they've got divided by 10 to the power 25. So you could, your graphs will look a little different. You'll see the gradients are the same, but your intercept might be a bit different. But whichever one you use, so they want a gradient, you'll get about 3.9 or 4. They say 2 or 3 sig figs. Of course, no units because it's a log versus log. There'll be no units. And apparently, you should get around there for your L value. Okay? Okay, and this is paper 2, Advanced Physics 2. This is Edexcel 2017. This is what it's meant by a standard candle. Okay, it's just a reference that we've got, and let's be a little. You write something a little more detailed. It's a reference object that we know how bright it is to something that's close. If something's really far away, is the brightness diminished because of the distance? So we go with something that's close by for reference. Okay, explain why trigonometric parallax is not used beyond a certain distance. I would imagine that, if I can draw a diagram here again, if that object is so far away, then you're not going to get much of an angular difference. You're not going to get much going on there. You can't use it. It's too far away. The angle would be too small.
We've tracked its trajectory. Parallax is headed for Oa.
Okay, the Earth's orbit is very small compared to that distance, and then I think that method we're going to get quite a bit of uncertainty. Okay, and then describe how a large distance is too large for the use of standard candles can be determined. What we'll typically do for this is we'll measure the wavelength of something. We'll see how much it's been red-shifted. Okay, the amount that it's been red-shifted, if we know how far the light's been shifted, we'll take a look at our emission spectra or an absorption spectra. You'll see how far the lines have shifted from something else. That amount of redshift tells us what its true velocity is, and because we know its true velocity, we can then use our graph with the Hubble constant. We can work our way backwards. Okay, and so if we've got velocity versus there's a graph here, and don't we have a formula? Here's our Hubble constant, and that's how we would go ahead and then calculate the distance from that using a Hubble constant. Okay, so it's a pretty straightforward 6-mark questions. Yeah, a standard candle, something we know what its luminosity is, so we can compare. If it's really far away, the parallax angle is too small. Okay, the Earth's orbit, and it's a very large percentage uncertainty. Okay, you can't just go ahead and say, oh, the angle's too small and leave it at that. It's 2 marks. So what's the problem with either of these things? Okay.
The Earth will be lost. We'll be ready to make a stand against parallax before it reaches Oa.
And then here, we measure the wavelength. You could do the frequency. You determine the velocity from the redshift, and then you use that formula. Okay. Straightforward. Okay, and I've got a Cambridge Pre-U question. This is from paper 3, 2016. We've got want us to show the graph of intensity of light. Now, a graph should look something like this. It's only 1 mark. We'll see. Okay, on to part B here. We've got the sun, and they give the surface temperature and its maximum wavelength, and then you've got a distant star, which its maximum wavelength, with its maximum wavelength, calculate the surface temperature of the star. Well, with Wien's law, we can set these two equal to each other, can't we? And we can just find the surface temperature of the one, and so we'll have lambda 1 over lambda 2, won't we? Right, and I get 14,361. Maybe for sig figs, I'll round up to 14,400. Notice I didn't mess around with units, because this is a ratio of wavelengths, and so the units won't matter, and it's just multiplying going to, in this case, increase the temperature. Okay. Using data from similar stars, it's estimated the surface area of a distant star is this. Okay, let's find the luminosity of this star. Well, this is from Stefan's law, so our luminosity should be equal to this equation here, and I get an answer here of 1.52, let's say, times 10 to the power of 27. Right? And then finally, intensity of the radiation they give. Calculate the distance of the star from the Earth. Luminosity is a unit of power. So we can say the intensity is power divided by, we know, the surface area. So we're gonna figure out what that distance is. R in this case is the distance. I suppose this could have been a D as well, whatever. Okay, so we will swap that up there. We'll get power over 4 pi times the intensity. Right, so partway through I got 7.559 times 10 to the 34. We'll take the square root, and I get a distance of 2.75 times 10 to the 17 meters. Let's check the mark scheme. Right. So we got the 14,400. We got the 1.5 times 10 to the 27, and we got the 2.75 times 10 to the 17. Lovely. I have a little bit of a problem with the description here. Rising from 0 to a peak and then falling away. I mean, for all we know, for that graph, we could just, we're rising to a peak and then falling away. This needs to be a specific shape, and I've seen in some mark schemes how they describe this slope is greater than this slope over here. This is kind of more dragged out, that sort of thing. Okay, we should be looking at shape something like this. This is what we're looking for. Mark scheme's pretty lazy there, but it's a 1 marker, so what can you do? Okay, moving on. I've got a paper 3 from the pre-U Cambridge, and this is a question about Hubble's law. State Hubble's law. You think of that graph that we've got there. We know that because it's a directly proportional graph, that recession velocity is meant to be directly proportional to the distance. Okay, so basically we're saying the further the galaxy is from us, the faster it's moving away, or you can say the recession velocity with which a galaxy is moving away from Earth is proportional to its distance, something along those lines. Explain the principles used by observers on Earth to determine the speeds of distant galaxies. Well, we use a redshift, right? We try to calculate the redshift of the spectral lines, and from there we try to figure out what the recession velocity is, and therefore we know how far away. That's how it's done. Let's check the mark scheme for those first 2. Okay, speed of galaxies is directly proportional to their distance from the Earth. Yes, we measure the wavelengths of the spectral lines, and the velocity is determined from the shift in wavelength from the redshift, something like that. Good, lovely. Okay, moving on. Describe how observations about distant galaxies provide evidence for the expanding universe. Well, we've said that we know that it seems from the redshift we can calculate what the speeds of these distant galaxies are. We can also do things to calculate the distance, and we do see that the galaxies which are the furthest away are moving the fastest. All right, and then moving on, how does this explain the Big Bang Theory? The Big Bang Theory is the idea that we started from a single point and this universe expanded outward. Well, if we see that in all directions these galaxies are moving away, and the universe is expanding, then that's evidence of the Big Bang Theory. These are kind of the same thing. This actually helps prove the Big Bang Theory, but they want to know the distance galaxies provides evidence. Okay, and so what they've said, galaxies are moving away. It implies from a point implies they originated at that point. Okay. All galaxies have been traveling the same time. Okay. That's one way to explain it. I know some exam boards will do one thing, other exam boards will do other things. Okay, and I've got an OCR, Physics B here. This is the science literacy, or the paper 2. And a question here about parallax.
According to Abin Sur's last transmission, he seemed to know what it was. His only words were, "It's parallax."
Okay, so they give us the parallax of Sirius arc seconds. Okay, they tell us, yeah, we know what a light year is. Yeah, that's fine. We're going to calculate the distance Sirius is in light years. Okay, if that's our arc length, and this is 1 astronomical unit, so we're looking for this. So we'll say, right, we'll say that theta in radians is going to be x over d, so we need to do d is x over theta. 1.5 times 10 to the 11 divided by, right, and technically, right, yeah, this is it's a sine theta, isn't it? Yeah, so we're going to do sine, but we need to what we need to do is we need to take our 38 seconds, we're going to divide that by 3600. That's going to give us the number in degrees. Okay, so it's a very small number, 1.05 repeated times 10 to the power of 4. That's a 4. Okay, and so we're going to do the sine of that. Okay, and so that gives me 1.8 times 10 to the negative 6. So do 1.5 times 10 to the power 11 divided by that. I get a pretty big number here, 8.142 times 10 to the power of 16, but we got to convert this into light years. So this is meters, isn't it? Yeah? Right? That's meters, because this was unitless and this was meter on top. So now we're going to have to convert that into a light year. Okay, well, they're telling us that a year is that many seconds. Could just say the speed of light times 3.2 to the 7. So I'll take that number and I'll just divide by 9.6 to the 15, and I get 8.48 light years. Explain why turbulence in the atmosphere limits the resolution of ground-based optical telescopes. Okay, I'm not sure what that's from if you need to read something, but you know, like we know that there'll be changing densities. Okay, and because the densities vary, you'll get different refractive indices, and so you'll get some, you know, images will be kind of wavy and blurry, and this is what happens. Okay, so fluctuations in air density because of the very different temperatures in the atmosphere, maybe something like that. Okay, all right. So that's question 10 and 11. Yeah, so we've done the calculation here. We got 8.5 light years. I think this is what I did. You could have, you could do this way. You could work with parsecs. You could do that if you like. That's fine. It ends up being 8.2 light years. You know, whatever. That's fine. On to 11. Different parts of atmosphere will have different refractive indices. Yes, leading to changing direction of light as it travels through the atmosphere. It gets a distorted image. Okay, that's fine. You don't even have to talk about why. There's different refractive indices. Okay, yeah, different air densities cause different refractions. Okay, but what happens is you need to say that that means it's going to change the direction of light as it travels, and your image is going to be distorted. Number 12 is about spectroscopic measurements of stellar distances. Describe how absorption spectra are formed and how they're useful in establishing spectral class of a star. You know, light's going to be absorbed by that gas. Certain atoms of that gas will absorb energy. It's going to promote electrons to a different level, a different orbital, but it needs to be of a certain wavelength. Okay, so if each absorption spectra is a certain fingerprint for what elements are in there, we kind of have an idea of, you know, what composition this is. And so if the stars, you know, doesn't have any lithium or iron in there from fusion, but it's only mostly hydrogen and helium, we know what kind of stage the star is in. If it's maybe got some heavier elements there, like carbon, oxygen, lithium, then we kind of maybe know where they're at. So that way we can kind of see where a star is along its life cycle, and we tend to know what temperature those stars are. Okay, explain how determining the value for the brightness leads to the measurement of distance. Oh, right, yeah, okay. So we know that the further the star is away, the less bright it will be. So if we know how bright something is, whether it's absolute or apparent, we can relate that to how far away the star is. Okay, it's generally inversely proportional to the square of the distance. Okay, the following example may help our explanation. Oh, okay, so what's that? Okay, X is 3 times the absolute brightness of star Y, but both appear equally bright in the sky. Okay, so, well, what does that mean then? It probably means, okay, so if we've got X and Y, and they're saying that X is got 3 times the brightness of Y, but they appear equally bright in the sky. Okay, they appear equally bright in the sky, but we know that star X is 3 times as bright. So that one's probably closer, we would say. Okay, distance to star Y has been measured to be 12 parsecs. What's the distance of this one? Alright, so this brightness unit, whatever that is, that's going to be the same up here. We don't know what this distance is. We can call it x. These are going to be squared, aren't they? And so, yeah, we've got 3 over x squared is equal to 1 over 12 squared. So we could do a little cross multiplication here, and we can see that x squared is equal to 3 times 144. And that gives us x of about, well, let's say 20.8 parsecs. Okay, so we've got 20.8 parsecs. Yeah, it's about 1.7. Oh, that's interesting. 1.73 times further away. What's 1.73? What's 1.73? It's the square root of 3. And we had said that it was 3 times as bright, didn't we? Okay. We see the brightness is proportional to 1 over the distance squared, don't we? Because we see that ratio there as being root 3. And it was 3 times brighter, wasn't it? Okay. You're going to want to do some calculations and then put it into English, because my answer here is not very coherent.
At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it. I award you no points, and may God have mercy on your soul. Okay.
So what would you say here? Okay. Description of absorption line formation, model of light within atoms, inverse square law. Okay. Yeah, I didn't even talk about inverse square law, but it's fairly obvious, isn't it? Okay. You need a well-developed line of reasoning which is clear and logically structured. Okay, what can we talk about? Well, I already talked a lot about the absorption spectra. We got the light travels through a cold gas. Okay, the gas. Certain frequencies are absorbed. I know a lot of exam boards like you to mention it is the atoms that absorb this frequency or wavelength of light. Okay, there's certain photons that are going to match specific energy levels. It's going to be unique for every element because every element has a different electron configuration in their orbitals. Different elements have different spectral lines because of different energy levels. Yeah, I just said that. And stars can be grouped into classes by their spectra, which gives a good indication of the absolute brightness. Okay, so that's where that comes from. And we see the inverse square law, brightness varies with the square root of the distance. And as we've seen that, we've done a calculation, recognition answer can be found from, well, we've just figured that out now, haven't we? Yeah? I'd said 20.8 divided by 12, but if I did 12 times root 3, I've got it. Okay? So what you could do is you could take your distance times the square root of this factor for your brightness, how much brighter it is, and you could get the distance from that. Okay, and that'll tell you how far away that star is, even though it's absolutely brighter, but still looks the same brightness as something else in the sky. It'll tell you what its distance is. Okay. Okay, I've got another paper 3 from the Cambridge Pre-U. This is June 2014. And, it's another number 7, and it's another one of these questions involving Wien's law. And you're just going to rearrange and solve for the temperature of the other star. Okay. Calculate the radius. Yes, Stefan's law, same thing. I'll pause. You can pause for a sec, get the numbers and plug them in, but let's go to take a look at the mark scheme. Right, real quick, those are your answers. So I hope you plugged in the numbers, got your answers. That's good. Let's move on.
Okay, I've got an OCR, modeling physics. This is the Physics A, paper 1. We'll skip past the energy levels and the emission spectra and that sort of stuff, although I do want to jump down here. So here's a hydrogen alpha emission line. I want to jump on down to 3 in the laboratory. The wavelength is this. Use this figure to determine the recession velocity. So we've got our ratio of the redshift with the laboratory wavelength. That's equal to the ratio of the velocities. We want the recession velocity, so we'll just multiply by the speed of light times this wavelength ratio. Okay, now this difference here, I measured it, and up above here I've measured it, I believe, to be halfway between 61 and 62. 661.5 minus 656.3. So that's a 5.2 nanometer difference divided by the original 656.3. So it looks like I get about a 2.37 times 10 to the power of 6. Suggests why hydrogen spectral lines play an important role in determining redshift of galaxies. Well, because stars are made of hydrogen. Hydrogen's very abundant. Hydrogen is going to be in the stars. For 1 mark, that's about all I would say. Right, abundance of hydrogen, good. 2.4 times 10 to the 6. Okay, I had said 2.37, but I think they'll accept anything within this range because it's coming off of the graph. That's fine. Okay, and you need to be between 661 and 662. So there we go. Okay, right. Light from a similar star is viewed in a galaxy further away. The star is part of a pair of stars which orbit a common center of mass. Describe and explain how the equivalent spectrum might appear. Right, so we've got a binary star system, there's a center of mass, and we've got these stars which kind of rotate around this center of mass. And we've seen questions like this, okay. How would the equivalent spectrum appear? Well, if you've got one star brighter than the other, then you will have, when the dimmer one comes in front, you will have a fluctuating intensity. So I would say, variable strength, variable brightness, variable intensity, that sort of thing. What else might we see? If this star is further away, what else can we say? If it's further away, we know from the inverse square law, probably it won't be as bright. I would say it's a dimmer, not as bright. It's not going to be as intense when it reaches Earth, okay? And since these galaxies are farther away, okay, we're talking about spectral lines, we're talking about spectrum, but we haven't mentioned it in this question anywhere, but we were talking about spectral lines and talking about redshift up here. So we're going to compare with the other one. These lines are going to be more redshifted. Why are they more redshifted? Well, they're further away. If they're further away, they're traveling faster. If they're traveling faster, they're more redshifted. Let's see. Okay, so less intense, not as bright. Galaxy is moving faster and therefore greater or longer wavelength. So more of a redshift, okay? So you could just say greater redshift, but I would say it's moving faster and therefore it's a greater redshift. Okay, and what's this? Periodic shift in wavelength if plane of orbit is in line of sight. Yeah, right, okay? So argument referring to splitting of not ideal blue, no blue shift. We're not worried about this star blue shifting as it moves away from us, because the whole system is moving away. It's a redshift, okay? But if our line of sight is in the plane of this orbit, we should see periodic shift in wavelength, okay? Right, and here we are, another binary star question. This is from OCR, the Unified Physics, which is a paper 3 of the Physics A. And stars are viewed from Earth in the plane of rotation. Stars are observed using light that has a wavelength of 656 nanometers. The observed light is shifted. Calculate the maximum change observed. Okay. So this is going to be, we're going to swing this up times our ratio of our speed of light there. Okay, but the question remains, what is the velocity? What is it? Well, they gave us the period. Our velocity is just going to be that circumference divided by the period there, right? So they gave us that radius. They told us the period, and there we go. So I got a velocity of 63,853 meters per second. So my shift is 0.14 nanometers, I believe. Let's check how we're doing so far. 0.14. Check on the right if you want to read there. You can pause and have a look. Okay, I've got a Fundamentals of Physics paper. This is the paper 1 from the OCR Physics B. And we've got these graphs here. Explain how these graphs show evidence that the universe started from a Big Bang explosion. Okay, I think for 2 marks we can do this really simply. What they want you to say is, hey, this graph tells us that, the further the distance these galaxies are from us, the greater their recession velocities. And this is meant this somehow proves that the universe started from one particular location, one single point, and they've been expanding out in all directions. That's what they want you to say there, I bet. And how do these graphs show that the universe started from a hot state? Okay, well, you might want to use the second graph here. Here's your cosmic background radiation. Okay, this is the wavelength. The wavelength is 1 millimeter. It's very small. It's microwave. The idea is that when the energy was released in the Big Bang explosion, this hot bang to start the universe, it would have been much, much higher energy levels. And energy, you know, is proportional to frequency. It is therefore inversely proportional to wavelength. And so if you would have had a shorter wavelength back then, it would have been hotter. We know things have been redshifted, and so it used to be a shorter wavelength. It used to be hotter. What are they saying? The graph shows proportional relationship between velocity and distance, and they kind of leap here. They say if galactic recession is played back in time, the galaxies were closer at the Big Bang. All was in the same location. All matter was in the same location. Shows straight line through. The graph shows a straight line through the origin. It means, I suppose, that the distance used to be zero. Maybe that's what they're saying. Maybe that's a way of getting a better way of explaining it. It meant that if the line is played back in time, the galaxies were all closer. The distance between all the galaxies at some point was zero since the line goes through the origin. Maybe that's the way you can get that now. Okay, you can't just say it's a straight line. You can't say it's Hubble's law. You can't say anything about correlation. But you could say, hey, if we reduce the distance down to zero, it means everything started together. And that would explain this Big Bang expansion. Okay, fine. I'm happy about that one. And the second bit, the graph shows background radiation is in the microwave region. It's 1 millimeter. Okay, thermal, you know. But if the radiation happened earlier, it would have had a shorter wavelength, which would have meant more energy, would have been hotter. Okay, and this radiation has been stretched by expansion because we see it's all cosmic microwave background radiation. That's kind of what I'd said there. Okay, you could say stretched redshift of the photons. Okay, right. Let's move on. Okay, so here we've got photons at peak intensity, have this energy at 5 kT. Use this approximation and data from that figure to find the temperature of the cosmic background microwave radiation. Well, I think the relative intensity we had said was at 1 millimeter, didn't we? Okay, and I had just been using this formula here. We're going to use it here. That energy is Planck's constant times the frequency is equal to 5 Boltzmann's constant times the temperature. We want to find the temperature. We're going to have HF over 5K. The frequency. What's the frequency?
What's the frequency?
Well, it's going to be the speed light divided by the wavelength. We said that was 1 millimeter, so that's 1 times 10 to the negative 3. That's 3 times 10 to the 8. Looks to me like we'll get 3 times 10 to the 11. And we'll plug this all in, Boltzmann's constant, Planck's constant, and you get a temperature of about 2.8. Okay, 1 millimeter off the graph, yes, 2.8. You plug your constants in and you're fine. There's some stuff there on the right if you want to pause and have a look. Okay, this question is from the component 2 Eduqas. It's a part of the WJEC, but it's the Eduqas version. This was from 2017. Okay, a binary star system consists of a low-mass star orbiting a far more massive neutron star. Okay. When analyzing light from the low-mass star, the hydrogen line, okay, yeah, has a Doppler shift, tells us, okay, further experimental measurements show that the orbital period, show that the radius of the low-mass star's orbit is approximately, okay, probably redshift means we will be finding the velocity of something, and we know the velocity is also equal to the circumference divided by the time, and that's the period. So maybe what we could do is we could say, hey, I'm going to plug these into each other. I'm going to say that the radius is equal to t over 2 pi times v. We know v is equal to c delta lambda over lambda. Let's plug it all in there. So I've got 1.45 years. You're going to have to do times 365 times 86,400. Maybe you do that separately. Maybe you do that there. Times c. They gave us the redshift. I'll plug that in. Okay. We'll divide by the 486, blah, blah, blah. And we've got a 2 by there. Let's plug it all in and see what we get. Right, and I get 2.3 times 10 to the 11. I'm kind of anxious about this. Let's see. 2.34 times 10 to the 11. Okay, good. Now, look it. You can do it in steps. You can do it like, okay, I'm gonna solve for V first. I'm gonna plug it in to this. I've done it all in one step, and I think it's just one calculation. It saves you time. If you do this calculation and you're writing this number down, and it's in your calculator already, you know, and then you're rearranging, you're writing all this out to, right? Look at, do you see how it's a little more efficient? I'll just rearrange one equation. Maybe I've done this maybe a little sloppily, but you can, you know, practice and improve. Get it into one equation. Do it one time, and I think it saves you a bit of time. Okay, and on the same paper, we've got a question here. And this is the kind of thing that's unique to WJEC. They're going to ask you to discuss the benefits and cost to society of such missions. This mission here was about the lacrosse, you know, impacted on the moon. Look, I'll let you pause and read that. You come up with two things that might be a good thing for why this could be, what the cost and benefits are, okay? Right, I've given you enough time, or you've unpaused it. What are the benefits? Okay, it's easier for humans to survive on the moon if water is present, to help understand the Earth-Moon system, to help advance science, create jobs, new technologies, generate interest in space exploration. A lot of technologies, a lot of things that we take for granted today are a result of stuff that was first used by astronauts. Sure. Costs. Funding would have to be used to address Earth-based issues, little current impact on society, pollution on the moon. Okay, so pros and cons. Do you think the benefits outweigh the costs? Okay, there might be a longer type question where you actually get into the more nitty-gritty, but this is a very Eduqas WJEC type thing. Okay, this is the AS Unit 1 paper from 2018 for WJEC. A black-body graph of spectral intensity against wavelength for a star, which I'm sure you've all seen before. It's magnified, and it shows these little spikes, and they are associated with the line spectrum. Explain how the graph and the spectra can be used to provide information about the star and the elements from which it's made. The graph and the spectra. Let's break this into what the graph can tell us and what the spectra can tell us. The graph can tell us at what wavelength is the peak wavelength for the most intense, okay, bit. And then from that, we can use that wavelength to figure out what the temperature is using Wien's law, okay? And so we can find out what the temperature of the star is, okay? We also know what color that wavelength is, yeah? Getting on to the spectral lines, well, each of these, each element has its own unique emission absorption spectra where these lines will be at certain wavelengths, okay? So we can, first of all, find out what element is in the star. We know most stars have certain, you know, we can tell by comparing with spectral lines for elements on Earth. First of all, we can see how far these lines have been redshifted, and therefore we can figure out how far away and how fast these galaxies or these stars are moving away. Okay, so we know the star, how far away it is from the redshift. Okay, but we can also figure out the composition. If we happen to detect that there's spectral lines for heavier elements, we can assume along what part of the life cycle of the star that the star that we are observing is in. Let's see what we've got for 6 marks. I don't know if I've covered it all there. Wavelength at peak intensity, and Wien's law can find out the surface temperature. Yeah, okay. Power emitted per square meter can be calculated using Stefan's law. Ah, right. Once we know the temperature, okay, I forgot that. Once we know the temperature, we can use Stefan's law to figure out the power being emitted. Okay, we can, as I said, the color of the star can be deduced from the wavelength. Okay, the line absorption spectrum is shown. All right. I didn't talk about whether it's emission or absorption. I just said in general, but you could say, hey, I see an absorption spectrum. You got a mark for that. You can say the spectral. All right. Yeah. Okay. Some exam boards will be picky about this. Where do these lines come from? They arise from passing, I've drawn this on a few questions already, passing light through a gas, the atoms of the gas. Don't say the gas absorbs the wavelengths. The atoms absorb these wavelengths of light. Certain photons, certain exact values, and that's why those lines are missing from the continuous spectrum. And this, now we can tell what elements are therefore present in the star. Okay? Other bits, the total area under the graph represents the total power radiated. Okay. Absorption spectra indicates temperature and generation of star, as we had alluded to, kind of what stage they're in, yeah. Redshift gives the radial, recessional velocity, and the distance we had said. And you could talk about an inverse square law on the distance, okay? So plenty of things there. I think I covered it all. I'm just trying to illustrate the thought process. Okay, well, what do we know? Let's talk about this. Let's talk about that. You're going to have to get the practice and write your solutions there, okay? Make sure you're practicing how to do these questions.
Okay, here we go. Yes, number 7 seems to be the astrophysics questions on the Cambridge Pre-U Paper 3s. Here we are from 2012. This is a question it looks to me about...
It's parallax.
Calculate the distance of star X from Earth. Right, so they're telling us that this is the orbital distance of the Earth. They're telling us that from January to July was 0.000051, so half of that's 0.0000255 radians. (1.5 times 10 to the 11 divided by sine). And then just be careful when you're typing this in. Make sure you get the correct number of zeros. It's a really high probability for error right there. I've got 3.37 times 10 to the 17. That seems, good. I've chose sine theta, but for really, really small angles, it should be known that sine theta is basically equal to tan theta. So you could have done tan. You could have said it opposite over adjacent. It's fine. Okay. Right, moving on. The luminous flux. Calculate the luminosity. Okay, so they give us the luminous flux here. That's the same thing as intensity. You know that intensity is power divided by our surface area. So that's going to be the power divided by pi r squared. They want the unit for luminosity. Okay, the luminosity is the same thing as the power. The luminous flux is how much power per square meter. So what we'll do, they want the luminosity. Okay, or you could say power. That's basically going to be the flux times the area. Plug in the numbers, the surface area of that sphere coming out, okay, at a certain radius, right? So we've got the radius here from up above. We're going to square that, multiply by 4 pi. Just plug that all in. 5.14 times 10 to the power of 27, and the unit should be watts. Looking at the mark scheme, yeah, we had that, and we just got that, and it's watts, okay, or joules per second. Okay, another star has the same luminosity, and its flux is measured to be this. Calculate the distance of y from Earth. Okay, so they have the same luminosity. We've just said luminosity or power. We said we'd have the intensity times the 4 pi r squared. And I'll label these as a 1, and then I2 times 4 pi r2 squared. The 4 pi's are going to cancel, aren't they? And really what's going on, so we want to find out what the distance is of the new one. We want r2 squared is going to be, it'll be a ratio of I1 over I2 times our original r squared there. So we'll just go back up to our original answer. If you were to read this question ahead of time, look at the part 1, look at the part 2, and then look at the part 3. See, the part 2 and 3 kind of rely on this value that we got for radius. You might save that number in your calculator, and then you can just boom plug it in later on for subsequent equations. So you're going to square that value. You're going to take this luminous flux, and you're going to take this luminous flux, and you're going to have a ratio, aren't you? Okay. So it looks to be, r squared, which I've already got in my calculator, times 3.6 times 10 to the negative 9 over 8.3 times 10 to the negative 11. So I got a big number. Okay, careful on your calculator here. I've done a few things I've messed up, but I've finally got it. Okay, yeah, so it's a big number, times 10 to the 36, but you're going to take the square root for that. And I end up with 2.2 times 10 to the 18. So I think that's what we need. Just watch what you're doing. Make sure you got your calculator buttons and brackets and using that exponent button, all the stuff you need to make sure you get the right answer.
I must have put a decimal point in the wrong place or something. I always do that. I always mess up some mundane detail.
Oh! Well, this is not a mundane detail, Michael!
Right, let's take a look here. We've got two different graphs. This one shows the intensity from the sun, and this is the intensity from Y. Right. Use these figures to figure out the surface temperature of Y. I think we're heading into Wien's law territory again. Here's for the sun, and this will be for Y, won't it? Okay, and we want to find the surface temperature of Y. So it's going to be a ratio of these wavelengths, these maximum wave intensity wavelengths. Now, so it's 800 for Y. So that's fine. Okay. Surface temperature of the sun is what? 5,000, 6,000? It tells us right here 5,800. I was going to guess 6,000, but hey, that's fine. Put that number they give us in, and then we've got to get what do we think? This is 600 here. Shall we say 500? Does it look to be halfway? It seems a little bit more. So maybe we would say, I don't know, 525? Let's just put 500 in. Okay, and there we go. So 5/8 times 5,800 looks to me 3,625. Let's check and see. Ooh.
Did that go the way you thought it was going to go? Nope.
So not 500. They did go a little higher, didn't they? I had said 525. That would have put me up to 3,800. They say it's 540. And then, okay. Hey, plus or minus 200. Ooh, that only takes us up to 3,700. 500 is not a good estimate, is it? And let's be smart about this, and this is a lesson to be learned, okay? This is 600 here. We see we're a little bit over. This would, right about there would be 500, okay? And this here would be about 550. So I wouldn't say it's 550, but even maybe my 500 is, well, my 525, I don't know if that would have got us in. They say 540. 525, as I said, put me at 3,806. I would have been within the plus or minus 200. Okay? Definitely you can't say that that's 500. It's somewhere above. Okay? So lesson learned on that one. And getting back to the previous answer, I think we had 2.2 times 10 to the 18, didn't we? Okay? Just some calculations, folks. Just got to get some practice in. Okay, that takes us up to about an hour, and we'll continue on with some more questions from across the various exam boards in part 2.